Thank you. I will be presenting on our Bluetooth and ultrasound-based indoor localization and mapping platform called ALPS, the Acoustic Location Processing System. This is a project that is done in collaboration with my colleagues Niranjini and Oliver and our advisors Bruno and Anthony. So since we are here at the indoor mapping and navigation session of the conference, I'm sure I can just skip over the indoor localization applications, since you probably already know what they are and you know how cool they are. So I'm just going to dive right into and give you a primer about the current localization approaches that are out there and give you a couple of example systems. So generally speaking, we can classify our localization systems into two broad categories. One of them are range-based systems, which rely on some distance being measured between known locations and a target. These systems include things like radar-based systems, ultrasonic-based systems, and also the global positioning system, GPS. Then we have, on the other hand, range-free systems, which do not measure distance. However, they rely on measuring natural phenomena such as Wi-Fi signal strength and then mapping a location to them. Other examples include visual light communication systems and inertial measurement unit-based systems. So back in 2012, I was here at SenSys presenting on our original ultrasonic ranging system for mobile devices. This, of course, is a range-based system, and the motivation behind it was and still is to bring sub-meter accurate indoor localization to off-the-shelf devices such as smartphones and tablets. The system uses a frequency range between 20 kilohertz and 21.5 kilohertz, which is just above the human hearing range, however, still within the range that smartphone microphones are sensitive to. The old system we used performed time difference of arrival ranging on the signals that it received to actually give you a location in the end. So this was our old system architecture. We have several transmitters which are spread out throughout the room. They all transmit ultrasound to a phone, which is able to determine its location based on time difference of arrival ranging from the received signals. There are several challenges that were associated with this system in order to make it practical. The first one is that transmitting omnidirectional ultrasonic signals is quite difficult. Why would we want omnidirectional ultrasonic signals? Well, in an installation, we want to minimize the amount of transmitters we have and maximize the coverage of the ultrasound that they transmit. And it turns out that with standard speakers, this is pretty difficult to do. Secondly, we noticed that there were big challenges in the installation and setup phase of the system. Our system relies on precisely measuring where the transmitters are in 3D space, and the old system was also hardwired, which just increased installation cost and made it very unwieldy. Our system, as most range-based systems, suffers from obstructions which can block transmitters. This year at the RTAS conference at CPS Week, we presented a paper which showed how to transition from going from time difference of arrival based signals to time of flight ranging, which allows us to reduce the amount of transmitters we need to obtain a location. So this allowed us to be okay with some transmitters being blocked, and we have further expanded on this property in this paper. Last but certainly not least, our system, again, as most ranging-based systems, suffers from measurement errors that are caused by multipath signals. So now I would like to introduce ALPS to you, the Acoustic Location Processing System. We went from this setup that you see here back in SenSys 2012. It was a hardwired setup, very unwieldy, to a nice embedded platform which can be easily deployed. This system was also featured at this year's indoor localization competition at the IPSN conference. It won first prize in the infrastructure-based category, and we're also going to be presenting a demo today, so I'd be happy to meet you all later and show you the system. For the rest of the talk, I will be going over a lot of the enhancements that we made to ALPS over the years to make it a much more practical system. The first being that we designed embedded hardware. This was our old setup. It consisted of a 10-channel audio DAC, home theater amplifiers, hardwired speakers. So it was very, very difficult to deploy this in any real scenario. Now we have these embedded beacons, and the beacons feature an ultrasonic transmission, hardware. They feature time synchronization via 802.15.4, and they still have a very cheap speaker which has an omnidirectional horn attached to it which is able to radiate ultrasound in an omnidirectional manner. If we look a little closer at the electronics, it's a very cheap system employing an 8-bit microprocessor from Atmel, which also features an onboard 802.15.4 radio. It has an audio codec from Texas Instruments, which is able to transmit our ultrasound and also receive ultrasound through the onboard microphone, and it also has an RF amplifier so that we can do long-range time synchronization over 802.15.4. So I just showed you that we have an omnidirectional horn and why this is important. If we look at the directivity pattern of a standard speaker, you will notice that if you go higher in frequency of a given signal, the more confined your directivity pattern gets. So in case of ultrasound, using a normal speaker, you'll be able to hear the signal only in a very confined area right at the sweet spot of the speaker. Of course, this is not ideal if we want to minimize the amount of speakers that we have in the environment. So we tested several speakers, two of which you can see the directivity patterns here. All speakers are vastly varying prices, vastly varying directivity patterns, but ideally what we would want to see from a speaker is this kind of an omnidirectional pattern both in the horizontal and the vertical axis. So what we did was we looked at several commercial omnidirectional speaker designs, we looked at the acoustics literature, and we also used several simulators to get an idea of how we can spread ultrasound in an omnidirectional manner. And what we came up with is this design here, which is a rotated speaker horn. Now, a speaker horn, all of us have probably already seen a horn speaker. It's essentially this thing here, which is a normal speaker, and it has this waveguide attached to it, which is designed to increase the overall efficiency of the speaker. And what we designed to make it omnidirectional is we essentially have horns which are rotated 360 degrees around a single point where the speaker transmits into. So there are several parameters about this horn that you can vary. The height of the mouth of the horn, the width of the throat of the horn, how many sectors you have in it, the angle, and so on and so forth. And we found that the best way to test this was to test it in real life. So we designed a automated directivity pattern measurement setup, which consists of an automatic telescope mount, which is this pan tilt mechanism that you can see here, where you mount a speaker onto it and it is able to remotely controlled step through various angles on the horizontal and the vertical axis. So every time it steps, it will angle the speaker slightly differently, and we are then able to take frequency response measurements at different angles automatically and then come up with a directivity pattern for how each of our designs performed. We came up with two different evaluation criteria for evaluating how our horn performed, and these were one, the directional distortion, which measures the deviation from omnidirectionality. This means how does the magnitude of the signal increase as we increase the angle. And also that we measured the frequency distortion, which measures the flatness of the frequency response of the horn. So ideally, we would, of course, want a flat frequency response since we are going across a certain bandwidth. Our system is also affected by varying frequency response. So how does our horn perform? Well, up on top, you can see the directivity patterns of the speaker without the horn. This is a very cheap piezo tweeter, which is about $250 in small quantities. On the bottom, you can see it with our horn attached. And what you will notice is that the signal is spread out more. It does not attenuate as much anymore at the extreme angles. The next enhancement that I would like to talk about is the improved data transmission that we have worked out in our new system. Originally, we modulated transmitter IDs, ID codes, onto the ultrasound carrier. Now we need to be able to identify which received ultrasound signal came from which transmitter. So the simple answer, or maybe not so simple answer, was to transmit the ID of the transmitter with each ranging signal. Now this worked fine. However, the downsides of this were that we had a very long packet length in ultrasound. You can only transmit very slowly, and this led to limited robustness. So we thought, yeah, ultrasound is very good for ranging. However, it's not so great for data transmission. So we decided on using Bluetooth Low Energy for this instead. Bluetooth Low Energy, of course, is contained on pretty much any modern smartphone, so it was an obvious choice to use that. So if you look at our system architecture now, we have pretty much the same thing, except the beacons all have BLE transmitters in them, and the phone is also going to receive BLE packets. We added this daughter board to our original ultrasound transmitter. It is simply a system on chip which also transmits BLE, which is time synchronized with our ultrasound transmissions. So in order to explain to you how all of this works, I'd like you to consider this two-speaker system where we have speaker A, speaker B, and receiver C. The speakers are time synchronized and they transmit identical ultrasound signals in different time slots. And receiver C will simply listen to these. However, receiver C is not time synchronized, so it listens asynchronously. Now, just by listening to these, the receiver will not be able to tell which signal originated from which transmitter. And this is where Bluetooth Low Energy comes in. We equip our transmitters with Bluetooth Low Energy. They send out Bluetooth Low Energy advertisement packets in continuous periods. And in these packets, we include a counter value. And this is important because the receiver is only able to receive Bluetooth packets for a very short time, about once a second. Now this is because smartphones generally time multiplex their Bluetooth Low Energy hardware with their Bluetooth Classic as well as their Wi-Fi hardware. So the phone listens asynchronously to Bluetooth as well. And what we want, in the end, what we want the phone to be able to do is essentially tell where this time zero was, where this slot started. And this is simply done by looking at the timer value that is continuously incremented in each Bluetooth packet, as we can see here, and is then received at some point. The phone simply looks at the timer value, subtracts that, and is then able to determine which ultrasound signal belonged to which slot and which slot belongs to which transmitter. So how does this perform in real life? There is, of course, some non-deterministic delay associated with receiving the BLE packet and then transferring it up to the application layer. And in order to test this, we hooked up a PPS output signal from a GPS transmitter, so a signal which has a change in state once every second. We hooked that up to the audio input of a phone, and we also hooked it up to a Bluetooth transmitter. Then we had the Bluetooth transmitter transmit, as I just explained, the timer value, and we tried to timestamp the transitions in the clock signal in the audio buffer of the phone. And what we found is with decreasing the advertisement interval of the Bluetooth packets, we were able to achieve pretty low latencies of jitter. If we look at a 100 millisecond advertisement interval, we had a worst case latency of 275 milliseconds. For a 50 millisecond advertisement interval, we had 169 milliseconds. And for a 20 millisecond interval, we had a 72 millisecond worst case jitter. Now, since our transmission slots for our ultrasound are around 100 milliseconds, the 20 millisecond advertisement interval was good enough for us to time synchronize our phone to the transmission slots. So the next thing I would like to talk about is how to simplify the system setup. There's a big problem with these systems. If you would like them to go mainstream, there's a huge cost associated with actually installing them. And that is because you need to determine the precise location of each beacon in 3D space. The user or the installer will need to do this, and this is a very time-consuming process. So what we looked at was how can we automate this, or this process, or at least make it semi-automatic, that the user can help determining the positions of the beacons without actually taking a measure, a ruler out, or taking out a laser rangefinder. So we developed this user-assisted mapping procedure, which works very well for smaller rooms. So in scenarios like deploying beacons in your local Starbucks or your local restaurant, this is a very good way to do it. And it also has a nice side effect in that it can also automatically determine the floor plan of the area where you are setting the system up. So I'll step through this mapping procedure, how it works. The first step is to simply put your beacons anywhere in the room. The only assumption that we make currently is that these beacons are all within line of sight of each other. The next thing that is done is the beacons perform inter-beacon ranging between themselves. As you may remember, I mentioned that the beacons all have a microphone on board, so they are able to communicate via ultrasound with each other and perform time-of-flight ranging. Now, once they do that, we know what the distances are between the beacons, and we get this plane where they must all be located on. However, at this point, we do not know where this plane is in 3D space and how it is oriented. So the next thing that we do is we synchronize the receiver to the transmitters. Now this is simply done in order to perform time-of-flight ranging, which simplifies our setup procedure so that you only need 3 transmitters instead of more than that. And in order to synchronize, we simply hold the phone at 0 distance to a transmitter. Transmitters are transmitting periodically, and if we hold it at 0 distance, we can synchronize the phone with the transmission cycle. Then the next thing we do is we define our z-axis. This is done by putting the phone at 3 points on the floor and performing ranging at these 3 points. So once we have these 3 points, we are able to fix this, this plane on the z-axis, so we know the height of each of the transmitters. The next thing we should do is we need to define our x and y axis, and we do this simply by taking 2 measurement points along either the x or the y, and this will then orient our plane in terms of the x and the y. So with this done, we are already able to determine the position of our transmitters. The next thing that we still need is we need to draw the floor plan. Now, since we have our transmitters already set up, we can simply perform localization at key points in the space. And by key points, I mean usually corners of the room. So we perform localization at the corners of the room. The software is able to draw lines between these points, and we have our floor plan. How well does this work? Well, we performed this in, I believe it was 8 different scenarios. One of them you can see here, where we performed the auto mapping procedure in a cafe scenario. We were able to localize our beacons within an average error of 18.2 centimeters, and we were able to localize the corners of the room within an average of 13 centimeter error with a maximum error of 25.2 centimeters. So definitely, especially for smaller scenarios where it is where you would want the user to set up the system themselves, this is a simple solution which can be done by the user deploying the system. So next, we'll move on to what to do with the system in underdetermined scenarios. Underdetermined scenario is where we have a phone receiver, we have several beacons, we want to localize the phone, however, we do not receive a signal from every beacon because, like here, one of them is blocked. So we only get 2 signals, which is not enough to find a unique location of the phone. So what do we do in this case? Well, we can rely on other localization sources that we have, in this case, the range-free, the IMU sensors on the phone, which are able to give you the general heading of the phone as well as the distance that a person travels as they take footsteps throughout the space. So we are able to take both of these localization inputs, fuse them together, and then obtain a better location estimate than we are able to do with just one. So just to give you an idea of how all of this performs, here we have a scenario where we took where we walked through a space, we took the blue path, and we only performed localization using the ALPS system. It is very good. It is mostly right on the line. So this is, if you hear all beacons, ALPS is enough. However, this is not the real world. Well, one additional thing we can do in terms of supplementing this is adding the IMU tracking to it. However, what you will see is we already have really good localization, so adding a more noisy source to the input doesn't really help us that much. However, if we have obstacles in the environment and ALPS is not able to give us a location at every point in the room, so for example here you can see that the location was not able to update because we blocked one of the transmitters. So in that case, our localization either doesn't update or it's vastly incorrect. So what we do is we supplement ALPS with the IMU data, and we're able to, instead of just jumping between these 2 points, we're able to follow this path along here, which is just based on IMU data. So what does the performance look like? On plots, you can see when there are no obstacles present, ALPS does a good job localizing, adding the IMU on the, which is the red line is the combined IMU and ALPS data. It makes near to no difference. However, once we have obstacles we add obstacles to the equation, ALPS degrades in performance. However, if we fuse IMU with ALPS, we get still very good localization performance. Okay, now lastly, moving on to multipath detection. As most range-based systems, when a transmitter emits an ultrasound signal, we will also receive several multipath copies off of it, which bounced off of walls near the phone. Now ALPS does a fairly good job at detecting these by itself by doing some signal processing. We are able to find the true signal amongst the multipath signals. And this, however, does assume that in the recording we received a true signal. We received a line of sight signal. However, what happens when we receive a signal where there is no line of sight signal? So in this case, there is no direct line of sight between the speaker and the phone. So what the signal that we will receive is probably bounced off somewhere, and we don't have a line of sight signal, in which case ALPS would try to find a line of sight signal, but it will identify a non-line of sight signal, which will throw off our localization. So in order to identify which signals are line of sight and not line of sight, we again introduce BLE to the mix, which has different signal propagation properties and also different attenuation characteristics. So BLE goes through walls. We are able to receive the signal here as well. It will be attenuated to some degree, and we are also able to receive the signal here, which will not be attenuated because it has a direct line of sight. So what we did is we took these properties, we took the ratio of the received ultrasound signal strength to the distance determined by ultrasound, and we took the ratio of the received Bluetooth signal strength to the Bluetooth low energy, the distance that was calculated by the phone, how close it was to the Bluetooth beacon. And we also looked at other potential features that we can determine whether a signal is line of sight or non-line of sight by looking at the delay spread of the received ultrasound signal. And we looked at all of these. We threw them into an SVM classifier, machine learning classifier, and we looked at the accuracy of how well it was able to detect line of sight from non-line of sight. And we determined that these two properties here gave us a very good accuracy of over 96%, where we only look at, again, the ultrasound and the BLE signal strength and the distance that was determined by these two. And if we look at how we would actually train the system on how to detect line of sight and non-line of sight, well, this would all be part of the setup procedure, where you would have an app which guides you through the setup process. It guides you through how to determine the beacon locations, and it also tells you take a non-line of sight signal, so block beacon 5 or something, and then it will be able to get training data for non-line of sight signals. If we look at how well our training, our system performed, We can see that as we increase the number of line-of-sight signals, the relative percentage to line-of-sight signals, we reduce the amount of false negatives that we received, and we also increase the overall detection accuracy. So in conclusion, I can say that for interlocalization systems to really take off and to be viable, we need them to be precise, we need them to be cheap, and we need them to be simple to install. And ALPS can tick all of these categories. It has cheap hardware, and it supports the user-assisted setup procedure. Secondly, ranging-based systems often suffer from multipath ranging error. And by incorporating our machine learning approach for filtering line-of-sight and non-line-of-sight signals, we are able to reduce the error caused by multipath propagation. And yes, now I'd be happy to answer any questions that you have.